Welcome to Cambridge IGCSE Physics, Lesson 24.1, What are waves? Today we explore fundamental wave concepts essential for understanding energy transfer in physics. This lesson forms part of the core content for Cambridge International General Certificate of Secondary Education Physics, Syllabus 0625. We'll discover how waves transfer energy without transferring matter, a principle that underlies many natural phenomena and technological applications. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, know that waves transfer energy without transferring matter. This fundamental principle distinguishes wave motion from particle motion. Second, understand waves as disturbances that propagate. This means waves are disruptions that travel through space or materials. Third, distinguish between wave motion and particle motion. Wave motion involves energy transfer while particles remain in position. These objectives align with Assessment Objective 1, focusing on scientific knowledge and understanding essential for Cambridge IGCSE success. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, waves, which means disturbances that transfer energy through space or matter. The key point is energy movement without matter movement. Second, energy transfer, which means movement of energy from one location to another. This occurs through wave motion without physical transport of material. Third, propagation, which means the spreading or transmission of waves through a medium. This describes how waves travel outward from their source. Understanding these terms precisely is crucial for Cambridge IGCSE success. Always use SI units, which stands for International System of Units, in all calculations. Let's explore our first core concept. The fundamental principle states that waves carry energy from source to receiver without transporting material. This means energy moves but matter stays in place. The definition is, a wave is a disturbance that propagates through space or a medium, transferring energy but not matter. Each term is important. Disturbance means disruption from equilibrium, propagates means spreads outward, energy means capacity to do work, matter means physical substance. Key evidence includes water waves moving energy across pond surfaces, while water particles only move up and down vertically. Sound waves transfer energy through air, while air molecules vibrate in place. The diagram illustrates this principle clearly, showing wave energy moving horizontally while particles move vertically only. Now we examine a standard demonstration following Cambridge IGCSE requirements. This slinky spring wave experiment clearly shows wave principles. The apparatus needed includes a slinky spring, which is a helical metal spring, a smooth floor surface for the spring to rest on, and measuring tape for distance measurements. The method consists of these steps. First, stretch the spring to approximately 2 meters length. Second, create a pulse by quickly pushing and pulling one end. Third, observe the pulse motion along the spring. Safety is paramount. Avoid overstretching the spring beyond its elastic limit. Ensure the working area is clear of obstacles. The key observation is that the pulse travels along the spring while individual coils return to their original positions, demonstrating energy transfer without matter transfer. Let's work through our first example. The problem states, a water wave transfers 50 joules of energy across a pond in 2.0 seconds. Calculate the power transferred by the wave. We are given energy equals 50 joules, time equals 2.0 seconds. We need to find the power transferred. Step 1. Write the equation. We use the power equation, which is P equals E divided by T, where P represents power measured in watts, E represents energy measured in joules, and T represents time measured in seconds. Step 2. Substitute the values. We write P equals 50 joules divided by 2.0 seconds. Step 3. Calculate. 50 divided by 2.0 equals 25. Step 4. State the answer. The power is 25 watts to two significant figures, using the SI unit watts for power. Example 2 applies wave principles to experimental data. The problem is, analyze wave pulse travel in a slinky experiment to determine wave speed. The data shows distance traveled equals 3.0 meters, time taken equals 1.5 seconds. Now we analyze systematically. First, identify the relationship. We need to find wave speed using distance and time measurements. Second, apply the speed equation. We use speed equals distance divided by time, where speed is measured in meters per second. Third, calculate the result. Speed equals 3.0 meters divided by 1.5 seconds, which gives 2.0 meters per second. Fourth, interpret the meaning. This speed represents how fast the wave pulse travels along the slinky spring. The graph shows the linear relationship between distance and time, confirming constant wave speed. Mathematical skills are crucial in wave physics. Let's examine 3 essential skills. First, speed equation rearrangement. When we need different variables, we rearrange algebraically. Starting with v equals d divided by t, where v means speed in meters per second, d means distance in meters, and t means time in seconds. To find distance, we multiply both sides by t, giving d equals v times t. To find time, we divide both sides by v, giving t equals d divided by v. Second, unit conversion. To convert kilometers to meters, multiply by 1,000. To convert minutes to seconds, multiply by 60. Third, significant figures. Match your answer precision to the given data precision. For example, if time is given as 2.0 seconds, this has 2 significant figures. So your final answer should also have 2 significant figures. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, a wave transfers 100 joules of energy in 5.0 seconds. Calculate the power transferred. This tests your understanding of the power equation. Question 2 is intermediate level. It states, a wave pulse travels 4.0 meters in 2.0 seconds. Find the wave speed. This requires you to apply the speed equation we've learned. Question 3 is advanced level. The question is, explain why particles don't move with the wave energy. This tests your conceptual understanding of wave motion versus particle motion. For all questions, remember to show you're working clearly, include SY units in every step, and check your answers make physical sense. Write your answers now before looking at the solutions. Wave principles power our modern world. Let's see how today's concepts apply in practice. In communications, radio waves transfer information across vast distances without moving any matter. The electromagnetic waves carry energy and data, while air molecules remain stationary. In medicine, ultrasound waves create detailed body images safely. High-frequency sound waves penetrate tissue, reflect from internal structures, and return to create images without harmful radiation. In seismology, earthquake waves are detected by monitoring stations worldwide. Seismic waves transfer energy through Earth's crust, allowing scientists to study earthquake locations and magnitudes. These applications demonstrate why wave physics matters. Career-wise, telecommunications engineers design communication systems, medical imaging specialists operate diagnostic equipment, and geological surveyors study Earth's structure using wave principles. Let's review the solutions systematically. For question 1, the answer is 20 watts. We use P equals E divided by T, substituting 100 joules divided by 5.0 seconds, giving 20 watts. This is reasonable for wave power transfer. For question 2, we find 2.0 meters per second. Using V equals D divided by T, we substitute 4.0 meters divided by 2.0 seconds, giving 2.0 meters per second. This speed is typical for mechanical waves. For question 3, particles oscillate about equilibrium positions while wave energy propagates forward. This explains why matter doesn't travel with wave energy. Now, exam success tips. First, always show you're working step by step. Even with wrong final answers, you earn marks for correct methods. Second, include SY units in every calculation step. Third, check if answers are reasonable. Unrealistic values suggest calculation errors. Fourth, understand command words. Calculate means find numerical answers. Explain means give scientific reasons. Let's summarize today's essential concepts. The key points to remember are, first, energy transfer. Waves carry energy from source to receiver without transporting matter. This fundamental principle distinguishes wave motion from particle motion and explains how energy travels through space and materials. Second, wave motion. Disturbances propagate outward, while individual particles oscillate about their equilibrium positions. The wave travels, but the medium remains in place. Third, applications. Wave principles enable modern technology, including communications, medical imaging, and seismic monitoring. These applications demonstrate the practical importance of wave physics. For further study, review wave definitions and ensure you understand each term completely. Practice calculation problems, always including SY units and showing complete working. The next lesson covers wave properties, which builds on today's foundation by examining amplitude, wavelength, and frequency. Ensure you understand today's concepts before progressing, as wave physics builds systematically.